For the last 15 years, we treated the internet like magic. If a startup needed more computing power, a developer clicked a button and the infrastructure stretched to meet them. The cloud was an invisible, perfectly elastic resource. Then, generative AI models began requiring millions of sequential calculations running simultaneously, around the clock. This triggered a shift into what analysts call Cloud 3.0, a trillion-dollar infrastructure supercycle that broke the elasticity we relied on. This chart shows projected capital expenditures for the top 5 hyperscalers. To keep up with AI demand, companies like Amazon, Microsoft, and Google are committing up to $690 billion to physical infrastructure in 2026 alone. That eclipses their historical spending averages. Look at what happens when we overlay their operating cash flow. These companies are increasing their capital spending by roughly 70% a year, a rate that is now actively outpacing the cash they actually bring in from operations. The cloud is a physical machine made of copper, silicon, and steel, and it is currently accelerating into 3 rigid walls. The first wall is hardware. While the global supply chain can fabricate raw silicon wafers, the core bottleneck is a specific manufacturing step called chip-on-wafer-on-substrate, or CoWoS, the advanced packaging process that wires high-performance memory to the processor. Advanced packaging capacity is fully booked through mid-2027. For anyone trying to buy standard, high-density graphics chips, that translates to a 36 to 52-week waitlist. To bypass this monopoly and keep their data centers growing, the major cloud providers are taking the supply chain into their own hands. They are engineering their own bespoke silicon. This diagram breaks down the difference. A standard GPU handles a wide variety of tasks, but custom chips, like Google's Trillium, Amazon's Trainium 3, and Microsoft's Maya 200, use streamlined, high-efficiency pathways designed specifically for AI calculation. The demand for computation is forcing software companies to vertically integrate, turning themselves into hardware manufacturers to protect their development timelines. The second wall is power. A traditional cloud server rack draws about 5 to 10 kilowatts. An AI-optimized rack, packed with high-density chips and liquid cooling, requires between 40 and 120 kilowatts. This funnel illustrates the scale of the gridlock. A single AI facility now demands up to 1 full gigawatt of electricity, yet over 2,300 gigawatts of planned generation are stuck in a queue. Projects now spend an average of 5 years in the queue before they can plug into the grid. This delay has upended how infrastructure is planned. Developers are no longer optimizing for low network latency near fiber hubs. They are prioritizing speed to power, moving massive projects to energy-rich regions like Texas, simply because the electrons are available. But even those regional grids are reaching capacity. To secure dedicated, carbon-free baseload power that runs around the clock, hyperscalers are turning to nuclear energy. Microsoft is funding the restart of the 835-megawatt 3 Mile Island reactor. Google, meanwhile, has contracted a fleet of next-generation small modular reactors to power its upcoming campuses. The raw generation capacity of local electrical grids has become the definitive speed limit for artificial intelligence. The third wall is geopolitics. The physical cloud is now hitting hard legal borders. The United States Cloud Act claims jurisdiction over data held by American companies anywhere in the world. The European Union countered this with DORA and the EU AI Act, mandating absolute control over critical financial and health data within their territory. This friction has created an $80 billion market for the sovereign cloud, infrastructure built to isolate regional data from foreign influence. This map shows the highest compliance tier, SEAL Level 4. To reach this standard, the data center must be legally owned by a European entity, operated only by local citizens, and physically walled off from any outside access. Strictly enforced physical borders now dictate exactly where a global enterprise can build its infrastructure. This version of the Internet, Cloud 3.0, is deeply regionalized, heavy, and bound by both physics and law. The scale of this machine is projected to hit a $3.5 trillion valuation by 2035, providing the underlying intelligence for over 3 billion smart devices worldwide. To sustain that scale, we are building a uniquely modern infrastructure, bespoke nuclear reactors powering custom silicon chips, guarded behind national borders. The digital realm is expanding faster than ever in history, but its success depends entirely on our ability to engineer and master the physical one.